In this lesson, I will show you how to find the area that is squeezed between two curves. By the end of this lesson, you should be able to identify the region bound between two given curves, find points of intersection given two curves algebraically and also with a graphing calculator, and when appropriate, set up an integral with respect to x that will yield the area between two curves. Understand when finding the area between two curves will require the setup of two separate integrals. A few things for you to understand before we get started. This lesson has a prereq that students be able to graph any basic function by hand, including horizontal and vertical shifts, stretches, shrinks, and reflection. Basic functions include linear, quadratic, cubic, and square root, cubic root, exponential, log, rational, trig, and absolute value functions. So these are functions that you should be very familiar with. Also, this lesson also has a prereq that you are able to find points of intersection between two curves on a calculator and use the store function, STO, which is right here. So far, we have been interested in finding the sine area between the function and the x-axis. So perhaps this is f and this is the x-axis. We want to know what's the area below the curve. Now we're interested in finding the area bounded between two or more different functions. So perhaps we're interested in finding the area that is bounded between these two curves. Let's say this is the f function and this is the g function. So those are the two curves, and we are interested in finding this area, and hence the name area between two curves. What is the area between these two curves? What is that area, right? Not area below f, but area bounded by the two curves. So it turns out that it's actually not hard to figure that out. The area between two curves, provided that the top curve is always larger or higher than the bottom curve in the domain of a to b, is defined to be the definite integral from a to b. So from a to b, the f function minus the g function. Now remember that the f function must always be the larger function and the g function must always be the smaller function. Another way to think of this is to think of the area bounded between two curves is found by taking the definite integral of the top curve minus the bottom curve. Okay, so top minus bottom. Now, if the graph is not provided, we must draw a rough sketch to determine which function is on top and which function is on the bottom, because this is only true if there is a function that's strictly greater than the other. If the functions alternate between top and bottom on the given interval, multiple integrals may be needed to find the area. So you might have to set up multiple integrals in order to find the area. If an interval is not provided, we will have to algebraically or graphically determine the points of intersection to find the limits of integration. So we will go through one of those examples for you to see. Now let's take a look at our very first example on how to find the area squeezed between two curves. So find the area between this curve and that curve onto interval of 1 to 3. So the first thing you want to do is you want to look at each curve and determine which curve is on top. Okay? The first function is x squared minus 4x plus 10. This is a quadratic function that opens up. So you have to know the basic shape of quadratic, linear, cubic, log, and all these functions. So this is the first function. This is the other function, which is another parabola or quadratic function that opens down. The reason why it opens down is because there is a negative in front of x squared. So it's pointing to this curve right here. It is pointing to, so this second function is this guy down here. So this is that guy, 4x minus x squared. And then this is the top guy, which is x squared minus 4x plus 10. Top function, bottom function. We want to know the area from 1 to 3. So the first thing I'll do is I'll kind of sketch the region that we're interested in finding the area for. So I want to know what is the area in this region. That's my goal, right? So what I have done is I identified the top function and the bottom function. And the next thing I do is I set up an integral from 1 to 3, top minus bottom. So here we go. So area is from 1 to 3, y1 minus y2 dx. All right? Now we must be very careful when we do this, because it is possible to make a mistake on these signs. So top function minus the bottom function. So notice that because the bottom function contains more than one term, I put them in parentheses, and that afterward I would have to distribute my my minus sign. So x squared minus 4x plus 10 minus 4x plus x squared dx. Now we simplify that, and it becomes the x squared. There are now 2x squares, so 2x squares minus 8x plus 10 dx. Now to find this, we find the antiderivative of the inside function, evaluated at 3, and then evaluated at 1. Now the antiderivative is going to be x to the third over 3, and don't forget the 2 there, minus 4x squared plus 10x. Okay, so now I'm going to evaluate that at 3, and I'm going to evaluate that at 1, and then I subtract the 2. To save some time, I'm going to store my antiderivative function in here. So 2x raised to the third power divided by 3 minus 4x squared plus 10x. I'm going to go out here to my main screen, and I'm going to store the number 3 inside my graphing calculator. Hit 3, stow, and then x, and that allows us to store the number 3. Now we are going to evaluate the antiderivative at 3. So vars, y vars, function, option y1, enter, and that gives us 12. Okay, we're going to store 1 inside our graphing calculator. So 1 store x, and that stored 1 into a graphing calculator. Now we are going to evaluate that using the antiderivative function, and that gives us 6.667. So this is about 6 2/3. And so the last thing we do is we subtract these. We subtract the two numbers, we subtract them, and we get our area. And if we did, we get 5 1/3. So the area, when we subtract these two numbers, is 5 1/3. That's the area between two curves. All right. Here is another problem. You need to know, we're interested in finding the area between these two curves. So we're interested in finding this area, but first we have to identify which functions on top and which functions on the bottom. Now in this region, the function that's clearly on top is this line that's on top. So the line is this function. This is the line, so we are going to call that y1. Okay. Now the function that's on the bottom is this quadratic function, because in the region we're interested in, it's below the line. So therefore this is the function we call, this is the bottom function. Okay. Now we are going to set up an integral to find the area. So the area is the integral. Now it is obvious that the upper bound, going from left to right, the upper bound is 5, but I'm not even sure what the lower bound is. So that's what I have to find later. So we'll put a question mark there for now. We take the top function minus the bottom function, like this, dx. So the first thing we'll need to do is we'll need to find that lower bound and see where it is, right? Because and where the lower bound is where the two graphs actually meet. That's where we're interested in. Okay, so we'll have to go back to our graphing calculator, and we're going to type in both of these functions, x minus 12 followed by x squared minus 5x minus 7. We set our window to be from 0 to 3 because that's all we care about. Where do they intersect? Which is okay. So go ahead and hit graph. I shouldn't have hit graph because it seems like the y value will be below -10, so I will need to change my y window as well. So go back here and then resize your y window from -15 to -10, and that kind of gives you an idea where they're going to intersect. So they are going to intersect right there. See, right there, that's where the intersection is. We kind of zoom in, so that's why we get such a nice graph. Now we go ahead and we calculate their intersection. This is our first curve, this is our second curve, and we calculate the intersection, and the intersection happens to be at 1. So now we know the intersection happens at 1. So therefore, we know that our lower bound is at 1. And so we continue the process of finding the area. So the top function is y1, so we call that x minus 12, right? Because that's above the other function. Minus, this is the bottom function, and because the bottom function contained more than one term, we will need to put it in the parentheses and distribute the minus sign. So x minus 12 minus x squared plus 5x plus 7 dx. Now simplify this a little bit more. We get minus x squared plus 6x minus 5 dx. So same thing, we need to find the antiderivative, evaluate that at 5, and then subtract that to the antiderivative, evaluate at 1. So the antiderivative is negative x to the third over 3 plus 3x squared minus 5x. So to save time, I will use a calculator to evaluate f at 5 and also f at 1. So go back here and clear those. Type in the antiderivative function, which is negative x to the third. Divide that by 3 plus 3x squared minus 5x. Leave the screen. Take 5 and store that. So 5 store x. Evaluated at 5, and that gives us 8 1/3. Do the same thing for the next number. Store that. Evaluate that at 1, and that gives us negative 2 1/3. Now we're subtracting these two, so when you subtract a negative number, that becomes an addition problem. So the answer to this problem, which is the area between that region, is going to be 10 2/3. Alright, it is also possible for us to find the area bounded between 3 curves. So this is one of those examples where it is bounded between 3 curves. So the first thing we'll need to do is we need to identify which is which. So to make things simple, I will first begin by okay, well, let's go and identify the curve. Well, the first curve that I noticed here is that there are 2 lines. So here's one of them and here's another line. Now, one is steeper than the other, so we expect one of the two to have a higher slope, which happens to be this guy. So this guy has a higher slope. So this guy belongs to let's label that guy as y equals to 2x, because that guy is steeper than the guy to its right. So the guy to its right has to be y equals to x, because these are lines, right? These are lines. So that leaves us to the last curve, which is the curve 2 over x squared. So this is the curve 2 over x squared. Now we have identified three curves, and the next thing we do is we're interested in finding the area in this region. But as you can see, the area in that region involves three curves. The formula, or the way to find the area squeezed between two curves, the way how to find the area between curves can only happen two at a time. So then we kind of have to split this region up. So in the first region, let's call this the A region, and let's call the next region the B region. Okay. Now in the A region, so let's go ahead and set up the area for that. So area for the A region. Now area for the A region involves this line, and it involves the other line. Okay. Now this line is on top of this line. As you can see, this line is always higher than that line. So that line has a bigger output than that line. So in the first region, our integral will be from integral, let me name this y1, y2, and then y3 appropriately. So for the area of region A, it will be from y1 minus y2 dy. Okay. Now based on the drawing, based on the sketch that's given to us, we can kind of see that the point where the two lines in the point where the cutoff for our first area is going to be at 1. So that's where we kind of want it, right? It starts at 0 and it moves to 1, so from 0 to 1. So that's the area of the region A. So why don't we find that right now, and then we'll see what happens. So this is from 0 to 1. y1 is 2x, y2 is x, and then dx, okay, dx. Now continuing to work with this, we get 0, 1. 2x take away x is x, dx. So we find the antiderivative, and we evaluate that at 1, take away at 0. So the antiderivative for x is x squared over 2. We evaluate that at 1, we get 1/2. We evaluate that at 0, we get 0. So the area of region A is 1/2, because 1/2 take away 0 is 1/2. All right, so what's the area of region B? Well, the area of region B, we will need to identify the two curves associated with region B. Now, by looking at it, this curve is on top, and this little curve right here is on the bottom, right? On top and bottom. So in this region that we desire, this is the top portion and this is the bottom portion. Okay, so the top portion actually belongs to y3. So set up an integral from 1, and we'll need to find the upper bound. Y3 is the top curve, y2 is actually the bottom curve, y2 dx. Okay, so now where do they intersect? Because that's where we want to integrate to. So we have to take our graphing calculator, and we will have to program these two curves in here. So the first one's x squared, and the second one is x there, and we want to make sure that our window is in the appropriate output. So from 1 to 2, that's fine. Now the output should be from anywhere from 0 to 3, right? So we program it from 0 to 3 so that we can see it better. Okay, that's where the two curves will meet. So we go second, calculate the intersection, first curve, second curve, they meet at 1.259. Okay, so 1.26. Okay, so there you go. We got that. Now we go 1.26. y3 will be 2 over x squared minus y2 will be x dx. And then we do the same thing. We find the antiderivative, evaluate that at 1.26 minus the antiderivative, evaluate that at 1, and we're good to go. To save us some time, I'm going to use a calculator to finish this problem. So math 9, I want to integrate from 1 to 1.26, and then my first function is 2 over x squared. My second function is x with respect to x, and that gives me 0.118. Add that to 0.5 that I found in the area of A, so 0.119. So the total area is going to be 0.619. Okay, 0.619. All right. The area of the region bounded by the lines x equals to 0 and x equals to 2 and y equals to 0, and the curve x over 2 is, well, we first need to sketch this function. So we are going to sketch this function like that. Now here's x equals to 0. So x equals to 0. This is x equals to 0. This is the line x equals to 0. This is the line x equals to 2, right? X equals to 0. X equals to 0. X equals to 2. And then y equals to 0. So here is the line y equals to 0. Okay. And then the graph of the curve y equals to e to the x over 2. So y equals to e to the x over 2. Now, perhaps it's a good idea to just take a look at what this function looks like. Now, you don't really need to see the graph of the function to finish this problem, but it might be helpful. So the graph of the function looks like that, right? So here's a function. It will look something like this, like that. So we're interested in finding the area that's squeezed between the curves. So here, as you can see, the top function is that e to the x over 2 function. Now the bottom function is just this function y equals to 0. So that's the bottom function, y equals to 0. And we're interested in the area from 0 to 2 dx. And there it is. So we go ahead, and so this boils down to the area, to just a regular area problem. So we find the derivative, right? We find its derivative, evaluate that at 2 and at 0. So what is the antiderivative of this function? The antiderivative is going to be, we take it's itself, okay, and then you multiply by 1 over its derivative. Now its derivative is 1/2, and 1 over 1/2 is 2. So that's the antiderivative. Evaluate that at 2, and if we evaluate that at 2, we get 2 f at 2 equals to 2e, and then f at 0 will equal to 2. So the area for this, when we plug 0 in there, we get e to the 1, which equals 2. So the area for that region is going to be 2e minus 2, and this is 2e minus 2.